So, welcome back for this outing. As for what I told you yesterday, today for the electric dipole, we will deal in the equatorial axis. Okay, electric field at the equatorial axis, which lies in the equatorial plane of the dipole. So I make a rough sketch of the dipole, minus q, plus q, okay, and I take a point at a distance x away from it, from the center. Okay, so if you see, because this is bifurcating axis, it is the equatorial axis, so this point subtends the same angle at minus q as well as at plus q. Okay. So according to the geometry, I have A over here and x is the distance from point O to the point P under consideration. Okay, let's call this as point P. Okay, point P, anything like that, right? So according to geometry, by using the Pythagoras theorem, the base square plus the perpendicular square is equal to the hypotenuse square, so that this hypotenuse becomes equal to a square plus x square. This side also I've shown. Now, because of minus q, the electric field I have shown to be towards minus q like this, and that because of the plus q like this. Okay, there is an element of symmetry, and if I draw a line parallel to this line over here, okay, P is from minus q to plus q. Okay, this is small p, of course, which is the dipole moment vector. Anyway, so what I find is that if I resolve this electric field along this direction, then this will be the value of the electric field E plus into cos of theta and E minus into cos of theta, and I've taken both E plus and E minus to be equal to E naught. Therefore, this becomes equal to 2 E naught cos of theta. Something which I have shown over here in a blown up diagram. Okay, the same thing I have blown up. Okay, so that you can see properly. There, the component which is perpendicular to these components, the cosine theta components, they are E naught sine of theta and E naught sine of theta, which are opposite to each other, equal in magnitude, and therefore they cancel out each other. Okay, so we cancel out these components. So the component which is of, the total value which is of interest, E naught cos of theta plus E naught cos of theta is equal to 2 E naught cos of theta. Now let us write from the definition of electric field due to a single charge, E plus I can write as 1 upon 4 pi epsilon naught q upon a square plus x square under root whole square, which is equal to a square plus x square. This I take as E naught. Again, just like that, you can do anything with the symbols till we understand the things we have to understand, and E minus similarly is also equal to E minus is equal to E. Cos of theta, well, let us take this as theta, and this is the base, this is the perpendicular, and this is the hypotenuse. Cos of theta is equal to base upon hypotenuse, so it turns out to be equal to a divided by a square plus x square under root. So now that we get 2 E naught cos of theta, so let us write the value of the electric field in the equatorial axis equatorial axis, which is called broadside on position. This point could be here, this point could be here. Okay? Anyway, in both cases, we will find that the net value will be right to left, whereas the p value is from left to right as per definition. So that's why I am writing that the cap vector of E equatorial axis is minus p cap. Okay. So I have this equation, and now if I substitute the values, then 2 E naught cos of theta, so 2 q upon 4 pi epsilon naught a square plus x square into a upon a square plus x square under root. Now p is equal to how much? 2a into q. 2a into q. So this is the magnitude of the dipole moment vector. So I find that 2qa or 2aq is equal to p. So I can write here p upon 4 pi epsilon naught a square plus x square into a square plus x square under root. This becomes equal to a square plus x square raised to the power of 3 by 2. No problem. Now if, like before, x is very very large as compared to a, okay, which is normally the case, because the distance between the two dipoles 2a is very small, either for a natural dipole or for an induced one. Okay. So this I can write as approximately equal to p upon 4 pi epsilon naught into, this becomes equal to x square into 3 by 2, which is x cubed. In the condition that x is very very large as compared to a. So this shows that EA, the value is proportional to 1 upon x cubed, like it was before in the other case. But if we take that, then here the value is p upon 4 pi epsilon naught x cubed, and there in the end on position or on the axis of the dipole, it was, the result was 2p upon 4 pi epsilon naught x cubed. So I have one value, in this case p upon 4 pi epsilon naught x cubed, and in the other case it is 2p. Bear in mind that this is twice, this value is twice 4 pi epsilon naught x cubed. So that does with this axis also. And what I must tell you is, before I go to dipole in uniform field, I must tell you something, that the magnitude of the electric field which is found due to the dipole for x, this turns out to be proportional to 1 upon x cubed. Okay, this is proportional to 1 upon x cubed. If I try to draw a similar thing for 1 upon x square, then I must get a something maybe okay, this is proportional to 1 upon x square. So you can see that the electric field due to a single charge, it vanishes not as fast as that due to the dipole. In the case of dipoles, the fall of the electric field, here I can take the electric field and this is how it happens. Just to give you an idea of what is there for the case of proportional to 1 upon x, this case, then the graph goes like this. In all cases, the graph, this point vanishes, becomes 0, asymptotically becomes 0, asymptotically becomes 0, asymptotically this side also or this side also. Okay, so this is about, of course, I can take any point, for example here, okay, and then I can calculate the field due to negative charge like this, and this is like this, and I can take then the mean of the value and calculate it in terms of the angle, etc. Geometrically also it's possible to do it analytically using the mathematical tools. This kind of a thing I also did for you a couple of lectures before, okay, when I took positive and positive charge and positive and negative charge. So it has been nothing but a repeat performance, but because it is important, that is why I elaborated on that, did it again for you, and hope that you, okay. So the next item that I am going to come is dipole in a uniform external electric field. So next item is the electric dipole in an external field, and here first of all we are taking a uniform external electric field. Look here, this is my dipole, minus q plus q separated by 2a, and this line shows that this is actually, I have shown here that this is basically the dipole moment vector, okay, dipole moment vector P, whose magnitude turns out to be equal to, okay, 2a into q, right? So I put it in electric field, which is uniform everywhere. So this electric field will put a force on the positive charge, which is shown like this, QE, F plus, and minus QE, which I am taking as F minus. Both these forces are equal to each other, okay. So net force on the system is equal to 0, okay. And if I just take the vertical line over here, the angle that the dipole makes is equal to theta, then this angle also becomes equal to theta, and this angle becomes pi by 2 minus theta, and then the separation between the two, perpendicular distance between the two forces, which constitute, what will they constitute? They will constitute a torque. So the perpendicular distance turns out to be equal to 2a sine theta, okay. In fact 2a cos of pi by 2 minus theta, which turns out to be equal to sine theta, okay. So I see that these two forces are equal in magnitude but anti-parallel, okay, anti-parallel. They give rise to a torque. The net force is equal to 0, but there is a torque, and the magnitude of the torque will be equal to one of the forces multiplied by the separation between the two forces, not depending upon whether we are taking here or where, but the independent of the value of the center of mass, etc. So magnitude of the torque becomes equal to QE, which is the magnitude of the force, multiplied by the perpendicular distance between these two forces, which turns out to be equal to PE sine of theta, which is P is equal to 2a into q as per definition. And because the torque is like this, therefore the torque must point, so that I am showing the torque cap will be out of the board. Okay, in keeping with the definition of cross product. So what we find is that the torque is equal to P cross E, where the magnitude of the torque becomes equal to PE sin theta. Okay, of course F net is equal to 0. And what does the torque try? The torque tries to bring the dipole parallel to the direction of the electric field. So this is the purpose of the torque here. Okay. The net force is equal to 0. If the electric field at different points is different, that is non-uniform electric field, then there will be a torque also and there will be a force also. Okay. Now let us take the case of an increasing electric field. Increasing not with time, but as we move from left hand side to the right hand side, the value keeps on increasing. So in the first instance here, I have put the P is parallel to the increasing electric field. Okay. You can see that because the value of the electric field is smaller at this point than at this point. Okay. Then the force F plus will be larger in magnitude to the force F minus, and therefore the net force will be in the direction, and this and the P, they will be parallel to each other. Okay. But if I keep this dipole anti-parallel, that is the dipole axis, dipole moment vector is like this and the increasing electric field is like this, then in that case the force on the negative charge will be more or less compared to the force on the positive charge, and therefore the net charge is net force is anti-parallel. It is the same direction, but it is opposite to the electric field. Okay, so this is the case of increasing. Similarly, if the field were decreasing, then we can argue out that the results will become just opposite. Okay, so this is the case. Of course, fields can vary with time also, but right now we will not do that. One thing I have to mention to you, and that should be borne in mind clearly, that this dipole or this dipole or this dipole, whatever, they are taken to be permanent dipoles, meaning thereby that they are not affected by the external electric field here or here in all the cases, because electric fields do make changes in the dipoles. As I told you, that the center of the positive and the center of negative may be separated, and the moment they are separated, then what we call is, this is because of the external electric field, and we call it the induced dipole system. Induced dipole moment will appear. Okay, so this is with the electric dipole in a uniform and non-uniform electric field. So next item we talk about is the continuous charge distributions and how to calculate the cumulative value of the electric field due to such distributions. The distributions are of three kinds. A linear, where we define a linear charge density delta Q upon delta L in coulombs per meter. Surface, which is sigma, the charge density delta Q upon delta S, coulomb per meter square. In the case of the volumes, small volume elements delta V are taken, and the volume density of the charge is taken as rho delta Q upon delta V coulomb per meter cube. Okay. When we work out the electric field, okay, I'm just taking not delta L and delta S and delta V, but dl, ds, dv, okay, and under the condition that it is like that, okay, is very small, then the value of d can be written as 1 upon 4 pi epsilon naught delta L upon r squared sigma ds upon lambda dl upon r square, sigma ds upon r square, rho dv upon r square, etc., where the mapping has to be done by us. Okay. And these calculations, then what we get the electric field, the magnitude of the electric field, by integrating this whole thing with dl, this whole thing with ds, and this whole thing with dv. Applying the offshoots of the Coulomb's law, which is the equation for the electric field, and the principle of superposition, okay, and we are able to calculate these things. I am not going to indulge myself right now in examples which I may return and make some calculations which we do with the help of what is the Gauss law. The Gauss law, which is based on flux in and flux out, and of course which is easy to be done with symmetry properties. So next we return to the Gauss law, introduce the Gauss law, explain the Gauss law, etc. Okay, and for now I close the lecture over here. So what we have done, we have besides this, I took the broad on side position and the calculation, and then I put the electric dipole in an external field, which first I took to be uniform, and thereafter I took it to be increasing or decreasing, and I told you how in the cases and how the torque is there and how the force is there. So sometimes the torque is equal to 0 but the force is not, and sometimes the force is equal to 0 but the torque is not. Okay. So with that you can revise your torque, etc., from the lectures before and visit this lecture of today, and it will those things will help you in these things. So thank you very much. Meet you again. See you